Alrighty, lads and ladies, welcome back to Calc 1 Honors. Today is going to be a fun day. We've got a few kind of odds and ends that I want to share with you that are kind of nifty, some topics that we didn't get to look at as deeply as we did earlier in the semester. One totally fresh thing. And yeah, that's about it. So I'm going to prove for you today that the square root of 2 is irrational. I'm going to show you a connection between two different versions of the mean value theorem. I'm going to show you a really neat trick for calculating roots. And then the remainder of the class, if there's any time, we'll spend taking questions. We're going to kind of pivot to our review for the final today. So that's the roadmap, and Friday is going to be all review. So let's get started. I'm working in a different color today. I hope that this comes across okay. This is MAC2311, section OH1. It's a lecture. And today is the 21st of April, 2021. Today, I'm going to tell you a tale of two MVTs. You may remember the mean value theorem from earlier in the semester. We talked about it a little bit. I'm going to show you a second one. And we'll look at the connection between them. The other thing we're going to talk about here today is Newton's method, which is a root finding method. If any of you have a future in engineering, and I assume that a handful of you do, numerical methods are a very big deal. I'll tell you, even though I was interested in pure mathematics, numerical methods are so important that in my first few years of grad school, I was forced to take not one, not two, but 3 classes in numerical analysis. That's just how important that stuff is to the modern world. And then we will talk a little bit about the final. So before I go any deeper, I want to remind you when your final exam is, and pop up your syllabus here. Your final exam is 1 week from today. It's on the 28th, and it's from 10:30 to 12:30. So it is not our normal bat time. This is for 28/21 at 10:30 a.m. Please put this in your phone now. Do yourself the favor. All right, put it in your phone's calendar right now with an alarm or two, notification or two, at least an hour beforehand. Let me see, what else? Getting something. So the final, final of course is cumulative, meaning it covers everything. What else do we want to say about the final? It's going to be around 20 questions. With the same sort of distribution that we normally see. So like 10, 11, 12 of those questions will be free response, and then the remainder of them will be a 50-50 split between true, false, and multiple choice. I encourage you to look at the chapter reviews in the book, especially chapter 2. It's been a while since we dealt with the chapter 2 stuff. That's where we learned about limits, continuity, differentiability, talked about the limit definition of the derivative. Those are the sort of things that people tend to forget when it comes to the final. That's about all I intended to say here. But after we get through these other 2 topics, we can come back and take some questions about the final if you want. Okay. Recall back in chapter 4, we briefly talked about this thing called the mean value theorem, which says if f of x is continuous on the closed interval a, b, and differentiable the open interval AB, then there exists a number C between A and B such that f primed of C is equal to f of B minus f of A, all divided by B minus A. So this is the original mean value theorem. And there's a geometric interpretation. There are some kind of physics interpretations. I'm going to walk you briefly through those. The geometric interpretation is that if you look at the graph of the function f of x, this will be y equals f of x. This is the x-axis. And I'll just draw some kind of generic function in here. If you look at the graph of this guy from, say, A to B, like this, here's A and f of A, here's B and f of B. And you draw the secant line connecting the point on the left to the point on the right. The secant line is a line connecting 2 points on the graph. The slope of that secant line is the right-hand side of the mean value theorem. It's f of B minus f of A over B minus A. What the mean value theorem says is that somewhere in between A and B, and to my eye, it looks like one of them is right about here, there will be a number C where the tangent line is parallel to that secant line. So that's the original mean value theorem. It says if you give me a secant line, I can find you a tangent line that is parallel, and the point of tangency will be in between the two endpoints for the secant line. This is a shockingly big deal. It might not feel like a big deal because you guys didn't have a lot of homework questions or test questions on this. And that's because homework and test questions on this are always necessarily kind of contrived. You have to kind of force it. It doesn't feel like something you would want to do or care about. However, in a slightly more grown-up math class, the mean value theorem is the shit. This tool is so powerful for proving other theorems because it lets you go from an average rate of change, which is what this is, to an instantaneous rate of change, which is what this is. So it tells you, given an average rate of change, somewhere between there, your instantaneous rate of change had to match. And one of my favorite ways to think about this is on a hypothetical drive from Gainesville to Orlando. Gainesville and Orlando about 100 miles apart. If I want to drive from Santa Fe to Valencia, UF to UCF, I'm going about 100 miles. So imagine a cop in Gainesville sees me leave at noon, and a cop in Orlando sees me arrive at 1 p.m. I covered 100 miles in 1 hour. So my average rate of change was 100 miles an hour. Now, I wasn't going 100 miles an hour when I left Gainesville. You know, I was on Archer. Who would do that? Assholes. I wasn't going 100 miles when I arrived at Orlando, Continental or wherever. Again, assholes. But if my average speed over the whole journey is 100 miles an hour, those two cops, by communicating the time and the distance to each other, could deduce that at least at one moment in between those two, I was going 100 miles an hour. So the cop in Orlando could write me a speeding ticket, theoretically. And he could cite in court if I tried to challenge that ticket, saying, no, I was just going 50 miles an hour when I rolled into Orlando. It's bullshit. He didn't clock me at 100 miles an hour. He could go, aha, but by the mean value theorem, you covered 100 miles in 1 hour. At one moment in between, at least one moment in between, you had to be going 100 miles an hour. All right, the instantaneous rate of change, the slope of this tangent, has to match the average rate of change at least 1 point over that interval. Cool stuff, right? So this is the version of the mean value theorem that we talked about back in chapter 4. There is another version of the mean value theorem that you'll be seeing in more detail in Calc 2, but is rarely treated well there. And I think the right place to talk about it is now, because here we have the fundamental theorem of calculus that will show you how to connect the two things. So we call this equation right here equation 1. F prime of C equals f of B minus f of A over B minus A. We call that equation 1. The second version of the mean value theorem, I'm going to cover up the picture for this. It's called the mean value theorem for integrals. And it too has multiple interpretations, but I'm not going to go too deep into that. What I want to play around with are the hypotheses and the outputs from the theorem and see if we can connect them to each other. So MVT for integrals says if f of x is continuous on the closed interval AB, then hey, Bubba. No, but sorry about that. Then there exists a number C between A and B such that f of C is equal to 1 over B minus A times the integral from A to B of f of x dx. And I'm going to call this equation 2. And what I want to do is see if we can connect these two things to each other. I claim that these are equivalent statements. I claim that from one you could prove the other. If you assume the first is true, you could deduce that the second is true. And conversely, if you assume 2 is true, you could deduce that 1 is true. And compare the hypotheses. The first one says if blah, 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 then blah, blah, blah. And so does the second. So the ifs are the hypotheses. First guy says if f is continuous and differentiable, right? Continuous on the closed interval, differentiable on the open interval, then blah, blah, blah. The second guy says just if f is continuous, then blah, blah, blah. So first things first, let's look just at the equations. Remember, over here we have what's called an average rate of change, and this is an instantaneous rate of change. Over here, there is a name for this object. It's called the average value of the function, and this is a particular value of the function. I wonder if you guys see any relationships between the objects in equation 1 and equation 2. Are there any pieces that you can match up with one another? Any things that look similar? Any way to deduce 1 from 2 or 2 from 1? No wrong answers here. Just want to know what we're thinking. Yeah, notice the B minus A here and the B minus A here. So if I start trying to match pieces up, this f of B minus f of A needs to be somehow matched up with this integral. And also, this f primed of C needs to be matched up with this f of C. If I wanted to go from a statement about a derivative to a statement about the function itself, which direction along the differentiation chain am I going? To go from this to this, would I differentiate or anti-differentiate? Yeah, this would be an anti-differentiation thing. This f down here is an antiderivative for f primed. So let's try to think about this in the context of the fundamental theorem. By FTC2, if big F is an antiderivative for little f, then the integral from a to b of little f of x dx would be capital F of b minus capital F of a. Plugging this into equation 2, we get f of c is equal to 1 over b minus a times capital F of b minus capital F of a. And you should compare this to equation 1. All right, this is the same as saying f of c is equal to big F of b minus big F of a over b minus a. Compare 3 to 1. Every instance of a function is just swapped out for its antiderivative. And no, stop it. Stop it. I love you. Don't do it. Don't do it. Over here, f primed, his antiderivative is f. And over here, little f of b minus little f of a, is replaced by his antiderivative, big F of b minus big F of a. So 3 is saying the exact same thing as 1. And the thing that allows us to go from 2 to 3 is the fundamental theorem of calculus. So the fundamental theorem of calculus lets you convert the mean value theorem for integrals back into the regular mean value theorem. Nifty stuff, right? In other words, we just proved the mean value theorem from the mean value theorem for integrals. So they really are equivalent, or at least the second implies the first, and the first does imply the second also. We can go in that direction if you choose, but I think the fun thing here is to go in this direction using FTC2. There's something else that bothers me though, and should bother you as well. If you compare the regular mean value theorem to the mean value theorem for integrals, there's a difference in the hypotheses. The hypotheses for the first mean value theorem is continuity and differentiability. Little f needs to be both continuous and differentiable. The mean value theorem for integrals just has a continuity hypothesis. Can anybody tell me why that is? How do we get away from the need for little f to be differentiable in the mean value theorem for integrals? It's true that continuous functions have antiderivatives. Can we take that a little bit further? So what does that mean? Yeah, not every function is differentiable. But if you take a continuous function and you integrate it, you will get a differentiable function. This is FTC1. The way you prove this is by studying it as a function of the upper bound here, b. If I swap out this b for an x, I have 1 over x minus a times integral a to x, f of t dt. Or you just think of b as the variable. As a function of b, this is a differentiable function. Remember, FTC1 says if f is continuous, then the integral from a to x of f of t dt is differentiable. And its derivative is blah, blah, blah. So the fact that you're integrating in this version smooths the function and gets rid of the requirement that f start out differentiable. As long as this little guy inside here is continuous, then this thing, when regarded as a function of b, is differentiable. And you're able to relax that hypothesis. But the reason you're able to relax that hypothesis is FTC1. This question of when can I ignore certain hypotheses? When are they critical to the problem? When are they potentially unnecessary? Is a really big question in mathematics in general. If you have a theorem, you're trying to prove a theorem, you want this conclusion. You're like, I think under all circumstances, this thing is true. And then you investigate a little bit more closely and you realize, oh, well, not under all circumstances is this thing true. Only under certain conditions is this thing true. Those conditions are called the hypotheses. And you want to narrow those conditions down as much as possible until you find the exact situation in which this thing must be true. And it turns out here that the differentiability condition from the regular mean value theorem, which is a strong condition, remember, requiring a function to be differentiable is way more intense than requiring it to be continuous, is unnecessary because by FTC2, the integral of a continuous function is automatically differentiable. So beautiful stuff here, really, really beautiful stuff. I think seeing the connection between the two MVTs, the first mean value theorem and the second mean value theorem, is one of the best ways to see if you really understand what the fundamental theorems of calculus are saying. And that's why it's such a nice conversation to have at this point in the semester, because we've spent most of the term talking about derivatives and differentiability. We spent a good chunk of time seeing how to go from that via FTC into integrability. So I hope that you guys are feeling something neat here, that you're able to see the cool connection. And if you need to get this down, I would encourage you to write this down and try to make those connections if they're not already lighting up for you. It often takes time, and that's okay. All right. I'm gonna move on now. What does it mean to say a number is rational? What are rational numbers? Yeah, perfect, Tahara. Yeah. If x can be written as a over b, where a and b are both integers. What does it mean to say a number is irrational? Not necessarily. So the answer that came in through a DM there was that if it has a square root on the denominator, square roots are definitely connected to irrationality in big important ways. And that's actually where we're going with this. But like pi is also irrational, right? E is also irrational. So there are some numbers that don't have anything to do with square roots that are also irrational. Really, ir just means not. This prefix just means not rational. So if this isn't possible, if x can't be written as A over B for integers A and B. Not necessarily that B is 0, but just that there's no way to write this number as a fraction with whole numbers. So that's what irrational means. And there's other ways to think about it, right? Most of us are familiar with this idea of a decimal representation going on and on forever without any repeating patterns. But the technical definition of irrational is just not rational, i.e. not this. Cannot be written as a fraction A over B, where A and B are both whole numbers. So a number is called rational if you can write it as a fraction of whole numbers, and it's called irrational if you can't write it as a fraction of whole numbers. I would like to show you something quite beautiful, and that's the proof that the square root of 2 is irrational. Where we're going with this is towards something called Newton's method. Rational numbers, you can always compute them by just long dividing, right? If I want the decimal representation for 1/3, I can write, 1 over 3 and then do the long division, and I get 0.333333333, and that will give me a decimal representation for that rational number. And I can do that for any rational number: 5 over 6, 10 over 5, 7 over pi, well, not 7 over pi, 7 over 3. Any ratio of integers can be written in a repeating decimal or maybe a terminating decimal just by using long division. The place I'm going with this is, how do we find a decimal representation for the square root of 2? The answer to that is going to be Newton's method. But first, I'd like to show why it's irrational, why I can't just get there using regular long division. So here's the proof. One of the reasons I like this argument so much is because it's an argument by contradiction, which is a cool thing. You assume that your theorem is false, and then you arrive at something ridiculous, like 1 equals 0. If assuming your theorem to be false implies 1 equals 0, then the assumption your theorem was false must itself be incorrect, and hence your theorem is true. Does that make sense? So I'm going to assume that the root 2 is rational. This means that the square root of 2 is equal to A over B for integers A and B. A neat fact, we can also assume that A and B have no common divisors. Why? Well, because if they did have a common divisor, a common factor, then I could cancel that factor top to bottom. So in other words, I'm assuming that this is in lowest terms, right? That A and B share no common factors. If they do share a common factor, I just cancel them and get a new A and B. The number theoretic term for this is coprime, right? We say that A and B are coprime or share no prime divisors. It's a safe assumption. Every rational number can be written in lowest terms. So if the square root of 2 is rational, then I can write the square root of 2 as A over B in lowest terms. Sure, there would be other ways to write it, but I'm going to say I choose to work with the simplest fraction that is equal to the square root of 2. We're going to end up with a contradiction, which is going to tell us that that this assumption is incorrect. and hence the square root of 2 is irrational. So I'd like to ask you, how do you think we could end up at a contradiction if I begin with the fact that root 2 is equal to a over b, where a and b are in lowest terms? Then one way to arrive at a contradiction would be to show that a and b are a over b is not in lowest terms, that there is no way to write that in lowest terms, i.e., that any fraction representing the square root of 2 would have a shared divisor between the top and the bottom. That's precisely what we're going to do. If root 2 is equal to a over b, then 2 is equal to a squared over b squared. Square both sides. And this means that 2b squared is equal to a squared. Is everybody comfy with that statement on the right? The second one's actually an if and only if. It goes both ways. Now, if a squared is equal to 2b squared, then a squared must be divisible by 2. But I want you to think about how a square could be divisible by 2. It means a itself must be divisible by 2. Since 2 is a prime, the only way you can have the square of your number divisible by that prime is if that prime is in the original prime decomposition of your number, which means the square of that prime is in the prime decomposition of the square. A must be divisible by 2, i.e., a squared is actually divisible by 4. I want you to think about the logic here because it's really quite fun. It's a good exercise for your brain. If anything is equal to 2 times something else, it means that thing is even. So we're saying a squared is even. Think about the even square numbers. 4, 16, 36. Not only are they divisible by 2, they're all divisible by 4. And that's not a coincidence. Every even square is divisible by 4. And what this line says is that a squared is even. It's equal to 2 times something else. So that means a squared is actually equal to 4 times something else. So if a squared is divisible by 4, that means a squared is equal to 4 times some stuff. I don't know what the stuff is. It's some other integer. But that's what it means for an integer to be divisible by 4. It means when you divide a squared by 4, you get an integer. It's equal to 4 times something. So let me take that and plug it back in here. 2b squared is equal to a squared now says that 2b squared is equal to 4 times some stuff. And if you divide both sides by 2, you get that b squared is equal to 2 times something else. But this looks familiar. We're now saying that b squared is divisible by 2. Earlier, right, we said here a squared is equal to 2 times b squared. That means a squared is divisible by 2. Well, now I'm saying b squared is equal to 2 times something else. That means b squared is divisible by 2. But as with a and a squared, if b squared is divisible by 2, then b is divisible by 2. And now we're in trouble. So 2 divides a. In fact, right, 4 divides a. 2 divides a. And 2 also divides b. We've shown that 2 divides both a and b. And I claim that we can now declare victory, that we're done. Why? All right, so if a squared is divisible by 4, this means a, in particular, a is divisible by 2. Right here, I even wrote it here. A is divisible by 2. And down here, we've shown that b is divisible by 2. This is a problem, but it's a good problem. I want you to tell me why it's a problem. What I mean by good problem, right? Like I've got so much money, it doesn't fit in my bank account or in my home or under my mattress. Good problem. Perfect, it's contradictory. What does it contradict? And certainly there are multiple numbers out there that are divisible by 2. Why is it a problem that a is divisible by 2 and b is divisible by 2? What does it contradict? I can write a fraction where the top and bottom are both divisible by 2. How about 8 over 16? Or 12 over 24? Or 2 over 36? All those fractions I just listed, what do you notice about them? We're very, very close here. I'd like you guys to make this connection. I know you can do it. Look at the words that are on the page right now. I know there's a lot of them. Look towards the top. It's true. So what we've essentially shown is that both a and b are divisible by 2. I claim that that directly contradicts one of the sentences. In fact, the third sentence in the proof. We assume that we started with a fraction in lowest terms. Right. So any fraction of integers can be written in lowest terms. And we assumed at the start of this proof that we wrote this in lowest terms. But then we were able to show under these assumptions that a is divisible by 2 and b is divisible by 2. In other words, we weren't really in lowest terms, were we? But every rational number can be written in lowest terms. What we've just shown is that any representation of the square root of 2 as a fraction would have to have a common factor of 2 in the top and in the bottom. But it's an algebraic fact that every fraction of integers can be written in lowest terms. So if the square root of 2 can be written as a fraction, then it's impossible to put it in lowest terms. Is that possible? Fuck no. Every fraction can be put into lowest terms. So the assumption that's incorrect is that the square root of 2 can be written as a fraction. The square root of 2 is rational, is the incorrect assumption that leads to this contradiction. Hence, so this contradicts the assumption that A and B have no common divisors. Hence, square root of 2 can't be rational. And that is the end of the proof. So any rational number can be written in lowest terms. I assume at the start here that the square root of 2 is rational, and then say, okay, I'm going to write it in lowest terms. And then from that, I'm able to deduce that the top and bottom have to have a shared factor. If the top and bottom have a shared factor, then I wasn't in lowest terms, but that's always possible. So the thing that must have been impossible here was starting by saying the thing was rational. So the thing can't be rational. This fucked Pythagoras up big time, by the way. Really smart dude, but he believed that every number was rational. He believed that every number in the universe, all real numbers, he didn't call them that, but he believed that every possible length could be written as a ratio of integers. Maybe you need a really big denominator, you figure, but you always will get eventually you'll find a way to write any number as a ratio of integers. But here's an example of a number that cannot be written as a ratio of integers. It's impossible. The square root of 2 is the classic example, but of square root of 3, 5, square root of any prime. In fact, the square root of any number, any integer that is not a perfect square is going to be irrational. And you can use the same argument to show square root of 3, 5, 7, even the square root of 9, all are not rational numbers. Pi is also known to be irrational. And just 2 days ago, there was a new proof published on the irrationality of pi. It's a brand new argument. I can share it with you here, actually. I sent it out to the math department. I might still have it open in this browser. Yeah. This one's going to be a little bit beyond you guys right now, but if you save this link and read it at the end of next semester after you finish Calc 2, you'll be able to do it. Talks a bit about power series. Proving that pi is irrational is typically a very hard thing to do. I'm not aware of any other elementary arguments. They usually involve things like contour integration or references to big high-level theorems in number theory. This is the first elementary proof of the irrationality of pi that I've seen that doesn't lean on any really heavy machinery. It's a cool thing. Proofs that E are irrational. There's one nice elementary proof that E is irrational, published by Joseph Fourier in the early 20th century. But generally, irrationality proofs are pretty tough. There are a lot of important constants in mathematics whose rationality or irrationality is still not known. I have a great story about getting in a taxi cab here in Gainesville. The taxi driver turns around and asks, where are you going? I'm going to a math conference. Oh, that's cool. Tell me, by the way, is it known yet whether the Euler-Mascheroni constant is irrational? Like, what's this cabbie doing? So the joke is that Gainesville has a lot of unemployed analytic number theorists. But that's the proof that the square root of 2 is irrational. And it would be fun to see if we could generalize this to the square roots of other non-square integers, because it works just fine. The place I'm going with this is if this number is irrational, then I can't get a decimal representation by dividing the top by the bottom, because there's no way to write it as a top over a bottom with integers. So how do you get a decimal representation for the square root of 2? If I can't do it with long division, like I do 1/3 or 7/5, how do you do it? One good answer to that question is something called Newton's method. I'm going to turn the page. If root 2 is irrational, how do we find a decimal representation? The big answer here is that all real numbers, whether they are rational or not, can be approximated by rational numbers, meaning you can find a sequence of rational numbers whose decimal representations are known that gets as close as you want to that number. One way to find such a sequence for the square root of 2 is a tool called Newton's method. I'll show you the theorem and then I'm going to draw a picture. This says if x1 is reasonably close, and I'll come back to this, reasonably close to x, then the sequence of numbers x1, x2, x3, x4, and so on, defined by the rule xn is equal to xn minus 1 minus f of xn minus 1 over f primed of xn minus 1, where f of x is a function with a root. Well, let me call it reasonably close to x star, so I can make this special. F of x is originally as a function with x-intercept at x equals x star. Then this sequence of numbers will get closer and closer to x star. So Isaac Newton figured this out, and this formula is not insightful at all, but the picture is very insightful. So here's the picture. The point I'm trying to approximate is right here, x star. I take a guess, call it x1. Then I construct the tangent line to f of x. So this is the graph of f of x, which has an x-intercept at x star. That's the idea, is that it's a root finding algorithm. Then I construct the tangent line to f of x at my guess. So in this case, that would look like this. And then the place where that tangent line hits the x-axis, that's going to be my next guess, x2. And at that next guess, I construct the tangent line to my function. And I use its x-intercept as my next guess. Hard time drawing these tangent lines together. And I repeat this process. So the place where this guy hits the x-axis, this would be x3. And you see x1 is far away from x star, x2 is a little bit closer, x3 is much closer still. So this produces a sequence of x values that get closer and closer and closer to x star. What I want to do is use Newton's method to approximate the square root of 2. I'm going to use 4 iterations of Newton's method. So we're going to go x1, x2, x3, x4, and we'll get pretty close. So to use Newton's method, what do we need? Well, I need a function f that has an x-intercept at the number I'm interested in. And then we're going to take that function, find its derivative, and use this formula. Use 4 iterations of Newton's method to approximate the square root of 2. I get to choose the function I want. There's lots of functions that have the square root of 2 as an x-intercept, but kind of the dumb one, the obvious one, not dumb one, the obvious one is f of x equals x squared minus 2. Right? We know that this actually has 2 x-intercepts. One of them is the positive square root of 2, the other one is the negative square root of 2. So right over here is the square root of 2. The other one is the negative square root of 2 over here. I know that the square root of 2 is a little bit bigger than 1. And I'm going to use that as my first guess. So I start with a guess. That's a reasonably close guess. That's x1. And I'm going to here use 1. And then we look at the tangent line to this function, and we see where that tangent line hits the x-axis. That would be my second guess, x2. And all that formula does is it tells you the root of the next tangent line. So if f of x is x squared minus 2, then f primed of x is 2x. So according to my formula, x2 should be x1 minus f of x1 over f primed of x1, which is 1 minus, what is f of 1? That's 1 squared minus 2, which is negative 1 divided by f primed of 1 is 2. So this is 1 plus 1/2, which is 3/2, or 1.5. So the place where this tangent line hits right here is 1.5, this point right here. So then I'm going to construct the tangent line at 1.5 and see where that hits the x-axis. That's going to be even closer to the square root of 2. That's x3, and this would be x2 minus f of x2 divided by f primed of x2, which is 1.5 minus f of 1.5 divided by f primed of 1.5. And I'm going to get a little lazy with my arithmetic here. This is 1.5 minus, now what is f of 1.5? Let me use my calculator for this because I'm lazy. F of x is x squared minus 2, so I need 1.5 squared. And I need to subtract 2 from that. I get 0.25. So 0.25 divided by f primed of 1.5. Well, f primed of x is 2x. 2 times 1.5. I know that. That's just 3. So my next guess, my x3 is 1.5 minus, I'll put it in parentheses, 0.25 divided by 3. And this gets me 1.41666666. Which is already pretty good. But I can go a little bit further even. X4, I can do this as many times as I want, would be x3 minus f of x3 over f primed of x3. X3 is 1.416 repeating. I'll just write it as 1.4167. I'll round there at the 4th decimal place. Minus, what is f of x3? Well, that's 1.4167 squared minus 2. So what I'm going to do is I'm actually going to use, I'll use the rounded version. Why not? So 1.4167 squared minus 1. That's f of x3. And then I'm going to divide the, well, no, I'll just write it out like this. So this is 1.007. I'll leave it rounded there. Divided by f prime of x3 is just x3 times 2. So that's 2 times 1.4167. That's what goes downstairs here, 2.8334. And now I compute this number. So I've got 1.4167 minus paren 1.007 divided by 2.8334. And I get, oh, where did this go? Did I type this all right? This should be a little bit closer. Not, we're getting a little bit further, 1.0. That's right, 4. 1.4167 minus 7 divided by 2.83. Yeah, we're getting the same thing again. So here's the idea, right? X2 was right here. And then we would come up and make the tangent line. And then X3, it looks like after X3, we're actually wandering away. Is going to be right here where this tangent line hits. So I must have made some mistake in the computation there. But you see, even after 3 steps here, we're getting very, very good. I'm not sure what computational error I made in the 4th step. I can try it just one more time. Oh yeah, this should be a 2. I'm so stupid. All right, here. So this is going to be 1.4167 squared minus 2. That's my top, 0.007. So then I've got, for my x4, it's 1, so sorry, this is a 0. So then I'll compute this line, 1.4167 minus paren 0.007 divided by 2.834. There's our x4, 1.41422. We'll round it here as 1.41423. All right. So we can see in the picture, x1 is this first x value. Then we construct the tangent line that takes us over here. That's x2. That's the second x value. this guy, 1.5. Then we come up here, construct the tangent line. The x-intercept for that, that's x3, that's 1.416. This is getting very, very close to the square root of 2. And then x4 is going to get us even closer. I don't have anywhere near enough space to draw it in there, but I can show you in Desmos. I think I have a Newton's method thing here. Yeah, all right. So look at the picture. This is our function, right? X squared minus 2. If I take my first guess to be 1, I can show you what, sorry, I can get rid of all those. My first iteration of Newton's method looks like. So here it is. Let me turn off the second. This orange line is the tangent, and it hits the x-axis at 1.5. So that gives me my second guess as 1.5. And then I feed that back in, and I construct the tangent line there. Here's the tangent line at x equals 1.5. It's this green line. And I look and see where that intersects the x-axis. We can zoom way in here. And you see that it's very, very close to the actual root. The actual root is right here. And the root of the tangent line is right there. And if we want to, we can look at the third iteration. We did this computation. And you see now the blue line and the actual x-intercept for the black function, I can't even tell them apart. That's how accurate we get with just 3 iterations of Newton's method. But here we actually did 4. So this is an incredibly accurate representation for the square root of 2. If we ask our calculator, what is the square root of 2? Oops, sorry, not that. It gives me 1.142. 1.142. So this is how your calculator calculates square roots. This is the kind of simplest and most famous numerical method for a lot of these sort of things. Any algebraic number, any number that is the root of a polynomial can be calculated in this way. Again, Newton's method, like all the other numerical methods out there, and there are many of them, are kind of the foundation for the modern world. Differential equations is really kind of what all modern engineering is built around. And the way you solve differential equations in the real world usually is using a numerical method. I will teach you, if you take MAP2311.0H1 how to solve certain differential equations, but not most. Oh yeah, and Katie, thank you, you caught that. Yeah, that was the error. It should have been a -2. That's where I made the mistake here. We got the 1.007 instead of the 0.007. So that was exactly it. I goofed. All right, we are about out of time for today. We do have about 10 minutes left. So if there's anything in particular that you guys would like to see right now, as far as reviewing for the final is concerned, we can pivot to that. So the remainder of our class time this semester, whatever's left for today and all of Friday, is going to be review for the final. So is there anything from the homework or study guides or stuff like that that you guys would like to take a look at? The original graph from the theorem? Yeah, here we go. This is kind of a zoomed in picture. So we're trying to approximate this guy, x star. And the idea is we start by taking a guess. We look and see where that tangent line hits the x-axis. That becomes our new guess. Then we construct the tangent line to f there. See where that hits the x-axis. That is our new guess. The next step would be constructing the tangent line here and seeing where that hits the x-axis. Oh, actually, I just thought of something else I want to show you guys. I'll hold here for a few more seconds while it's drawing. What would have happened if I started with a guess over here, like -1? Would I have ended up getting closer and closer to this stuff? Or would it have done something else? Where is x3? x3 is this point right here. x4 isn't in this picture, but if we want to, because the picture would get cluttered, so I would come up here at x3, construct the tangent line, and see where that tangent line and we won't even be able to differentiate it between the this and the original, x4 would be right here, where that next tangent line hits the x-axis. So you take your guess, whatever guess you're at, you construct the tangent line to your function there, see where that tangent line hits the x-axis, that's your next guess. So the next guess would be x4, and that would be wherever the tangent line to f of x constructed at x3 hits the x-axis. And in this picture, we can't even really make it out from x star. If you want, I'll link you to this this Desmos thing here. This is actually pretty good. Spend some time on this, where you can follow as many iterations of Newton's method as you want. So here's the Desmos applet for Newton's method. I'll send it to everybody. It's pretty cool. You can look at as many iterations as you like, but Newton's method is so effective. Like just scroll down to first iteration, second iteration, third iteration. You can watch them one at a time. You can look at the things that make them go. The first iteration is here. Second iteration is here. Third iteration is here. Fourth iteration is here. And you can do this as many times as you want. But I want to come back to that question. If I started at -1 here, so I made that my first guess, I construct the tangent line here, I look at the x-intercepts, would that get me closer and closer to this number? Is the question clear? If I changed my first guess, instead of having x1 be 1 to having x1 be -1, would my Newton's method get me closer and closer to the square root of 2? Or would it get me closer and closer to something else? Don't add this to your picture, but let's look. Let's just look at what would happen here. So I would come down here, construct the tangent line. That would sling me back over here. This would be my next one. I would construct the tangent line, which would sling me back. That's not on the picture, but that would bring me back down over here. No, it would have me coming in closer and closer to this guy. So you can actually chop up the x-axis into two pieces. If your first guess came from anywhere over here, you would find yourself gravitating towards the square root of 2. If your first guess came from anywhere over here, you would find yourself gravitating towards the negative square root of 2. So the place that Newton's method takes you, this is that, remember to start with a reasonable guess. The place that Newton's method takes you depends on your first guess. This leads to a concept called a Newton fractal. You can do Newton's method in the complex plane. And if you do that, the complex plane will be broken up into pieces. If you take a first guess from any one of these green regions, like you take your first guess from this region over here, you will end up gravitating towards a point over here. If you take your first guess from any of these blue regions, you will end up, through Newton's method, going towards a point over here. So by splitting up the plane in the same way that I've said you can split up the real line here into two regions, if you take a guess from this yellow highlighter region, you will end up gravitating towards positive root 2. If you take a first guess from the orange highlighter region, you will end up gravitating towards negative root 2. If you study your function as a function of a complex variable, where the input is two-dimensional, you can do the same thing. You can color the input space according to where you end up with Newton's method. That creates these really beautiful pictures called Newton fractals. There's some of the simplest fractals to study. Fractals in general are very, very complicated. But these are somewhat easy to study because Newton's method is somewhat simple. The Wikipedia page here has a bunch of them, just for different functions. All right, so here's the Newton fractal for the polynomial x cubed minus 2x plus 2. That splits up the complex plane into a number of different regions, and they really are these fractal regions. They have this sort of really neat self-similarity. It's quite beautiful stuff. So if you're interested at all in fractal geometry, these are some of the easiest fractals to study, and they're also some of the most beautiful. They really are fascinating things. I invite you to check this shit out. You just pick your favorite polynomial, and you can generate a Newton fractal with that polynomial. The code to do so is in the Wikipedia page, I believe. All right. So that's where I'll leave it. This is fun stuff. There's a lot of fun things you can do with it. Nova fractals, this is actually new stuff. I don't know anything about Nova fractals. So you're looking at kind of a Julia set where you add an extra number in. That seems fun. But yeah, here they do have the code to implement this. If you wanted to try to run it yourself, it's a lot of fun. And that is all I have for you guys today. So I'm going to go ahead and chop it here. I would like on Friday for you guys to come with lots of questions. Remember, the final exam is exactly 1 week from today, 12:30 to 10:30. You need to put, 10:30 to 12:30. 1 week from today, 10:30 to 12:30. Please put it in your phones. Don't miss that shit. And on Friday, we will be reviewing for the final. So please take a look at the chapter reviews in the book, all of the study guides from the semester, all of the homeworks from the semester. See what you are nervous about on the final. Those would be the right things to ask about next class. Okay. Oh, I do see we have something in the chat here. I'm sorry, I don't want to ignore that quick question. Are you teaching Calc 2 this summer? I'm not doing a Calc 2 this summer. No, I'm doing a differential equations and pre-calc. But for Calc 2, I can strongly recommend the following people. Adam Christofferson, very, very good. Brandy Cook, she's good. Who else would I take for Calc 2? Angel Nieves, not bad. He's more of a physics interested person. Not quite my style, but he is very, very good. Who else is good for Calc 2? Send me a list. Send me a list of who you're considering, and I'll help you pick, or I'll tell you what I know about them. Alrighty, I'll see you guys on Friday. Have a good rest of your day.